So rules for random variables, and really what we're going to look at in this particular video, expected value and standard deviation associated with some of these. So expected value is a theoretical number. It's a theoretical value. So in the long run, if we keep doing something over and over and over again, what we would expect to occur um, if we were to take the average of all that, right? So we're actually going to end up doing a mean. And there's a formula for that. That formula, the expected value of that random variable that we've been discussing, is going to be just like other averages. It's a summation. What we're going to do is we're going to take each individual observation and we're going to multiply by the probability. So this is the individual observation, and this is the probability of the individual observation. And you're simply going to sum those together, sum all those products together, just like you would any other mean. So let's take a quick look at this particular example. You draw a card from a deck. If you get a red card, you don't win anything. So half the cards, you win nothing. If you get a spade, you win $5. And then for any club, you win $10. In addition to that, you get $20 for the ace of clubs. So here's the probability distribution for the random variable x. This would be the amount of money won that you're going to win. So the expected value, right? Find the expected amount you will win from playing this game. So to find that expected value, we're going to take $0. There's your first observation. You're going to multiply that by the probability. So this is x1, this is p1. There's x2 and the probability of 2. We're going to add that with $5 times 0.25. And we're going to keep doing this. So we got x3, we have a probability of that observation, 10 times 0.23, and then $30 times 0.02. And if you take a quick second and do that, you would see that the expected outcome is $4.15. So the big thing that you have to realize here, if I slide back, this is a theoretical value. This is what people would expect, right? So over time, some people win $0, some people win 5, some people win 10, some people win 30. So let's say that we had a bunch of people come into our obviously very simple card game, and as they walk away from the table, we jot down how much they won. So about half the people are going to win nothing. So as they walk away, $0. Some are going to win 5. So 10 people come along, and there's some zeros, there's some 5s, there's a few 10s, and maybe there's 130. Well, if we sum up that total and divide by 10, it's probably going to be pretty close to $4.15. The theoretical part comes in is if we could play this game an infinite number of times, then once we divide back out, again, theoretical, so we divide by infinity, we'd end up at $4.15. How that's helpful for us is we can think about how much one might want to charge for this game. So, right, let's say that we're trying to do some kind of fundraiser. Maybe we're running the casino, so we want to make money. We want to charge more than the expected outcome, but we also want to think about what's going to draw people in. Right? We could charge as much as we want. We could charge $100, but chances are, who's going to come play this game if we charge them $100 when all they can win is 30? For me, my thought, you might be a little bit different. I think $5 would be enough to draw people in. Right? You got a chance of breaking even, go and get your $5 back, or you could double your money, or you could win 6 times your money. That $5 allows at least half of the people, right? If you look back up here at $5, this whole group of people, so 5, 10, and 30, they're at least going to break even, if not win money. And you're still making a profit of about 85 cents per play. Some would argue maybe $10. My argument against $10 would be that at $10, only about a fourth of the people, if you look back up here, so at $10, only about a fourth of the people are even going to break even. A very, very small percentage would make any kind of money at $10 a pop. But if you made a coherent argument for $10, I could see it working. But for me, let's go a little bit over what we would expect. So we're making a little bit of money each time, and we're still low enough that people are going to be drawn in. That's my thought process. So, variance. is the square of the standard deviation. So we've seen before that variance is equal to the standard deviation squared. So in this particular case, our variance, just like before, this is how far, or this is the average distance from the mean. Another way of looking at it. So we're still going to be doing an average, right? We're going to sum a lot of things together, and then what you're going to end up doing, we're trying to see the distance from the mean, so we're going to take that individual observation and we're going to subtract the expected value. Right? We're going to square that, and then we're going to multiply that by the probability. The reason we're squaring is because we want to keep things positive right here. And then in order to get standard deviation, again, so if variance is standard deviation squared, and the square root of variance, is standard deviation. So if we want to find the standard deviation of this measure spread, all we're going to do then is take this value from above and take the square root. So again, if you're a little bit confused, why are we squaring that thing? Again, if we just simply took the average distances from the mean, you'd have some positive, some negative. So you'd end up with, when you added all those together, if we're the true standard deviation, the true average distance, by the time you add all the positives with all the negatives, it'd be 0. So we have to play this little math trick right here where we square those values, known as the variance. We get a numerical value, and then we work our way back to the standard deviation. Once we get this, we work our way back to the standard deviation by taking the square root. Right. So maybe we go back to our card game. So the variance for us, recall that the average winning was $4.15. So our variance was, so we take that observation, 0 minus 415 squared. We're going to multiply that by the probability. And then we're going to take the $5, subtract the expected value, right? This is the distance from the mean. Square that times 0.25. And then we're going to get the distance that $10 is from the mean times its probability. Excuse me. Let me clean that up just a little bit. 0.23. And then we're going to add in how far 30 is from the mean. We square it, and we multiply that by 0.02. That'll give us the variance. Now, what we want, we're going to look for standard deviation, and so it's a quick process. If this is the variance with all those numbers, if I simply take the square root of that entire value, then I get the standard deviation is, I believe, $5.48. So in other words, the typical amount of winnings is about $5.50 away from the mean, right? So if the mean was $4.15, if we go up or down $5.50, right, the typical value is going to be very, very close, somewhere between essentially 0 and $10, right? Most of the people, 98% of the people, are between 0 and $10, and we think about the typical distance from $4.15 plus or minus $5.50 essentially. It puts you really, really close to those two numbers. So there it is in context. Another quick example. A couple plans to have children until they get a girl, but they agree they will not have more than 3 children, even if they're all boys. So assuming boys and girls are as equally likely, so we take a quick second. So like, these are the 3 possibilities. You could have 1 child, 2 children, or 3 children. There's only one way to have 1 child, and that's to have a girl. To have 2 kids, you're going to start, you'd have to have a boy and then a girl. And then for 3, you could have a boy, and a girl, or you could have 3 boys in a row, which is the one a lot of people forget about. So we think about this. The probability of a girl is 0.5. Boy and girl, 0.5 times 0.5, which would be 0.25. And then if you take a quick second, that's 0.125, or, remember, we're going to add 0.125, and that's 0.25. So there's a 25% chance they have 3 children, right? So how many would they expect to have? The expected value here, 1 times 0.5 plus 2 times 0.25 plus 3 times 0.25 would be equal to 1.75 children. Common sense says that if they want to have a girl and it's a 50-50 shot, it's probably going to have pretty close, right? We're thinking if half of them are boys, half of them are girls, 2 children would probably give them a really, really good chance of having a girl. And that's what we see if we round there. The standard deviation, again, so we're going to take 1 minus 1.75, square that times 0.5, plus 2 minus 1.75, square that value times 0.25, plus 3 minus 1.75 squared times 0.25. And then remember, we're looking for standard deviation, so take the square root of that whole thing, and that's going to be 0.83. So one final example was the one with insurance, is a one with insurance policies. So if it costs $100 for the policy, and it's going to pay $10,000 for a major injury, $3,000 for a minor. And the company estimates that each year, so in a year-to-year basis, about 1 out of every 2,000 policyholders have a major injury, 1 in every 500 have a minor injury. So we're going to go ahead and create the probability model for profit. And once we get this probability model, we can start to figure out the expected profit and then the expected standard deviation. So, reason that we're here, most policies we're going to make $100 profit. But you think about right here, negative 9,900. Well, that's simply because if the company pays out $10,000, they've lost $9,900 of the original, right? Because the person pays 100, so the net there was negative 9,900. So this was for the major right? Major. Sorry, kind of putting this up together. That was for the major injury, and then a minor injury. They still paid the $100, but the company loses 3,000 for that net of negative 2,900. So the probability that these things occur, what we saw from before, right, that the major is 1 out of every 2,000. So 1 out of 2,000 would be 0.0005. And minor policies, 1 out of every 500. So 1 out of 500, 0.002. And because we know that these three values have to sum to be 1, we know this is 0.9975. All I did was subtract the previous two values from 1. Now, to get the expected value in standard deviation, we could go through with a formula. But really what we're looking at here, these values, these probabilities, this is the frequency that these things are occurring. So 99.75% of the time, right, that percentage of time, nobody needs a payout. So the frequency that the company just makes $100 and doesn't have to pay that out is over 99% of the time, right? 0.2% of the time, the company has to pay out. So the frequency that that occurs is very, very rare. Even less rare is this major injury, right? So what we can do is we can actually take advantage of the calculator, and in list 1, we'll put our profits, and then in list 2, we'll put our probabilities. And then when you set this thing up, excuse me, I'll clean that up a little bit so we can see it. Right? So there's list 1 and list 2 in the calculator. And what this is these are the values. This is how often it's occurring. This is a frequency list, which we've seen with one of our stats. So when you go into your one variable statistics, right, or one variable statistics, we can find mean and standard deviation using list 1, and then when you put comma list 2, this tells your calculator The first list that it puts is where it's getting the actual numbers, and in the second list, this is how often those values occur. And when we do that, we see that we get an X bar of $89. Excuse me. And then if you keep scrolling down, you see that whereas before we would see something there for um, the S of X, we don't see that now. But what we do see just below it, right, there's nothing, there's a few more things, and there's S of X, and there's nothing next of S of X. Well, that's because it's a sample. But we don't have a sample here. We have data on all of the policies. So in other words, we have information on the population, which is what that stands for. And so that 260.54, there's your standard deviation, and that X bar, there's your expected value. So your expected payout for every policy is $89, and the typical value, which in this particular case doesn't make a whole lot of sense, and that's simply because those extreme values happen at such a rare occurrence. It's very rare that somebody pays out that much money.